face recognition, object detection, and self-driving cars. Look at that. How the car is able to see everything around it using the numeric data of images. It kind of feels like that scene in the Matrix movie when Neo was able to see the code in everything around him. I hope after watching this video, you will also start seeing the numbers behind the images just like Neo. Because we are going to discuss exactly how the CNN algorithm works using a face recognition case study in Python, and we will go through the code line by line. I have also given the link to this case study from my website thinkingneuron.com in the description of this video for your reference. We will use the training folder images to train the CNN model and then use the testing folder images that are not seen by the model to check if it is able to recognize them correctly. Before you understand the CNN algorithm in depth, you need to quickly refresh your knowledge about how an image is stored in your computers or in your phones. This will also give you a context on how big a problem CNN has solved for us. Every screen that you see is made up of lot of tiny light emitting units called pixels. If the screen resolution is HD, then it has 1280 pixels horizontally and 720 pixels vertically. If the screen resolution is full HD, then it has 1920 pixels horizontally and 1080 pixels vertically. The more pixels you have on screen, the sharper and clearer the images will be. For example, the 4K resolution images are very sharp. Every image that is displayed on screen is a combination of multiple pixels with different colors. For example, look at this small face image of 500 by 500 pixels. If I zoom into the image, you might even see these tiny little squares. These squares are pixels. Every pixel has an overall color associated with it. The color of each pixel is determined by a combination of red, green, and blue colors subpixels. The intensity of red, green, and blue colors is defined by a number between 0 to 255. 0 being white and 255 being the highest intensity of that color. So when we look at the backend data for this image, we can see each row is a data for one pixel and it is defining the color of that pixel red, green, and blue. This means we are using 500 by 500 by 3, that is 750,000 numbers to store this tiny image on the laptop. Now this number quickly escalates. Today, we have camera phones with 50 megapixels as a common configuration. 100 megapixels, 200 megapixels are also present in some of the top-end phones like Samsung Galaxy S24 Ultra. So for a single image from your iPhone or any other 50 megapixels phone, you will have 157 million numbers stored in the backend. This is huge. Now imagine if we need to learn hundreds and thousands of such images via a neural network. Look at that. 786 billion values just for 5,000 images. The amount of computing resources required to scale up such a model will be too much, almost impractical. This is what researchers and scientists realized early on when they attempted to learn image data. They understood that they needed some algorithm to represent the images with a small set of numbers. And thanks to Jan LeCun and Kunihiko Fukushima, the OG scientists who invented the convolutional neural networks, we were blessed with an algorithm that took the most important part of an image and represented it with a smaller set of numbers. And if you bring a similar image, the numbers generated will also be similar. Like if I bring another face of the same person, then the numbers generated will be close to the ones generated for the first image. However, if I bring an image of a different person, then the numbers generated will be significantly different from the first person's number. Now, I can take this data, that is my input X, and use an artificial neural network to train the model against the output label Y, which is the name of the person. So when you give a new image to the model, it will convert it to numbers and then compare it with the numbers of all the other faces. And then it will give back the probabilities, like what is the probability of this image being Jessica or Sam. The final answer will be the face that gets the highest probability. This diagram shows the high-level architecture of how face recognition works. We take multiple pictures of each person and feed it to the CNN. You can put 5 or 10 or 15 images depending upon availability. The higher, the better. However, keep in mind that the more pictures you put in, the more time it will take to train the face recognition model. The CNN model generates numeric representation of each of the images. These number inputs is the X and the name of each person is Y. A classification neural network is used to learn this data. The same kind of architecture can be used to train CNN models to recognize rock, paper, scissors, cat, dog, mouse, or horse, left turn, right turn, straight road, speed breaker. All you need to do is to collect the images with correct names tagged to it. So now that you have seen the big picture, let's take a deep dive. Coming back to the image vector. Will the CNN algorithm always generate n numbers for an image? No, much more than that. And it depends on multiple factors like the original image size and the hyperparameter of the network. For example, look at this tiny image. This is 64 by 64 pixels. Now, before we understand how CNN represents this image, let us take a look at how it is stored on my laptop. So 64 pixels horizontally and 64 pixels vertically. The total number of pixels in this image will be 4096, 64 into 64. Now, how many numbers are required to store this image in the backend? So if you look at the backend array of the same image, it has the shape of 64 by 64 by 3. Why 3? So every pixel has an overall color to it. And the overall color is defined by 3 subpixels or 3 basic colors, the red, green, and blue colors. So these numbers are representing the intensity of red, green, and blue colors. And this one row is basically the information required to store 1 pixel. So the total amount of numbers required to store this image will be 12,288. Now, if I take this backend data and pass it to CNN, then it will represent the same image with 64 numbers. You can see the image vector generated by CNN is 64 numbers. By the way, do not worry about all of these code. I will explain each and every line as we progress through the case study. Right now, just focus on the concept that we are trying to understand, that CNN compresses the image and represent it with smaller set of numbers. So instead of using 12,288 numbers, CNN is using 64 numbers to represent this image. How CNN is doing that? It is taking the most important parts of this image and just representing those portions. Okay, so this is not exact same image. This is a representation associated with this image. And now the beauty is, if I bring another image of the same person, then the numbers generated will be similar. So this is not the same image. It is a similar image. Same person, but slightly different image. But if you look at the numbers generated, it will be similar to what we had previously for the same person. 59, 64, 10, 10, 17, 15, 26, 22, 3, 4, so on and so forth. You can literally see the overall numbers generated for one image will be similar to another image if it is of the same person, same face. Now if I bring another face, if I bring the face of another person, then the numbers generated will be different from the previous set of numbers. If you see 64, 76, 10, 17, 15, 28. So these are significant differences between the image vector generated for this person versus the image vector generated for this person. And this is exactly how we are able to distinguish between the images. Now if I bring another new face and the vector generated for that new face is close to these numbers, then I'll be able to say, okay, this is the image of this person, this man. And if the numbers generated for that new image will be close to these numbers, then I'll be able to say, oh, this is the image for this woman. So this is how I'll be able to recognize different faces using the CNN representation of images or the image vectors produced by CNN. Now, will it always generate 64 numbers? No. It depends upon the network configuration. So right now, the CNN that I have used here has certain hyperparameters associated with it. We will discuss all of these hyperparameters as we proceed further. Now let me change this. Let me change the last hyperparameter, let's say 4 cross 4 for the max pooling. Now instead of 64, it will be generating 128 numbers for this image. If I change it further, let's say if I use 2 cross 2 in the max pooling over here, then it will generate 768 numbers for the same image vector. Okay. So now, depending upon what hyperparameter you are using in your CNN, the shape and size of your image vector of CNN will vary or will change. Okay. Now, if you look at it, still it is a huge reduction from 12,288. We are representing this image using 768 numbers, or if I use a different set of hyperparameters, I can even represent the same image with just 64 numbers. That is a huge reduction in the amount of values required for me to represent the image. And this is exactly what CNN solved for us. Now, how exactly CNN is producing these numbers? How exactly it is taking these 12,000 numbers and converting it into either 768 or maybe 64 set of values? What happens within the CNN? What is this convolution, max pooling, and flattening step? Let's understand this one by one. The first one is the convolution step. This is the most important step of CNN because this is what really mimics the human eye, and it extracts the most important parts of an image. To understand convolution, let us first pay attention to the way you look at anything. How do you remember a person's face? When you meet with someone for the first time, you make a blurry image of that person in your head. You might remember one or two most important features of that person, like for this man, you may remember him as the French beard guy. This image gets clearer and clearer as you meet the person more number of times. You may now remember the details like moles or spots on the skin, etc. If you notice, at one point in time, you can only focus at one spot. The other parts of the image will look blurry. Try it. You may be focusing only on the eyes or the hair or the beard, etc. The other parts of the face will become blurred. Most of the times we don't even realize this, but when you do, it surprises you. So, in a way, we are scanning the person's face. In fact, our eyes continuously scan everything, and the more we look at something, the more details gets captured and better images created in our heads. This is what the convolution step tries to mimic. It scans the image by using a filter, one area at a time. The filter moves through the image and picks up the important features of that part of the image. If this filter is very small, then it can lead to overfitting because it is not able to generalize the image. If the filter is very large, then it can lead to underfitting because it will generalize the image too much. Hence, an apt size of the filter must be chosen. Exactly what size? I will discuss it shortly. Now, for the sake of explanation, let's assume this image is represented by a 6 cross 4 cross 3 matrix, one for each RGB channel. And we will look at the convolution operation in one of the channels. Let's say the red channel. The same operation will happen for blue and green channels as well. So this matrix of 6 cross 4 will be scanned by a filter. Popular sizes of the filter are 3 cross 3, 5 cross 5, 6 cross 4, etc. You choose the filter size based on your image size. If the dimension of the image is large, like 1000 by 1000 pixels, then you may choose a filter size of 10 by 10 or 20 by 10. Or if the image is small, like 500 by 500 pixels, then you may choose 5 cross 5 as well. It is a hyperparameter of the CNN algorithm known as kernel size. So you can start with any suitable value and then try different combinations to see which one is producing the highest accuracy. For the current explanation, let's choose a filter of 3 by 3. This filter is a 3 by 3 matrix with some numbers in it. But what does that mean? So imagine filters like your Instagram filters literally, because this is what happens when you apply a specific type of filter like gingham or moon or lark, etc. It basically changes the original image by changing the numbers of the stored pixels, and it does that by multiplying pixel numbers with the numbers of filter. So every filter has a specific set of numbers associated with it. Here, these 3x3 filter numbers are randomly generated by the CNN algorithm. So this filter is reducing the corner pixels because there are zeros present and stressing on the center pixels because it has a bigger number like 2. Some other filters may reduce the center pixels and stress more on the edges. So with every type of filter, you are actually looking at the image in a different way. Okay, how many filters should we use then? This also is one of the hyperparameters of the CNN algorithm. We can use 5, 10, 16, 32, 64, 128, basically any number of filters. However, we should start with a smaller value like 5 or 10 and keep increasing it till we get the highest accuracy. The important thing to keep in mind is the more filters we keep, the more computation is required for it, and it makes the model training slow. That is why it is recommended to choose lowest number that brings the highest accuracy. So what this filter will do is it will move across the image to scan it. And what is the scan operation? It is the multiplication of image numbers with the filter numbers, which is also known as the dot product. For example, when the filter is in this bottom right area, then the 9 numbers present in the 3 by 3 pixel area of the image will be multiplied by the 9 numbers of the 3 by 3 filter, and it will generate one single number, 22. This process will be repeated till the whole image is covered. The result of this will be a much smaller matrix as compared to the original image. This is known as the feature map or the activation map. Each of these numbers represent the crux of one part of the image. This 9 represents this area. This 24 represents this area, etc. As you can see, there is already a huge reduction in the overall image size. From 6 cross 4, it came down to 4 cross 2. The size of this feature map depends on the input image size and the filter size. An easy way to calculate the size is by subtracting the corresponding filter dimensions from the image dimensions and adding 1 to it. So over here it is 6 minus 3 plus 1 is equal to 4, and 4 minus 3 plus 1 is equal to 2. So 4 cross 2. Now this feature map was generated for the red channel. Similarly, two more feature maps will be generated, one for green channel and one for blue channel, and the values will be added together to generate a final feature map. So will the same 3 cross 3 filter matrix be applied to all the channels? No. There will be a 3 cross 3 filter matrix for each channel correspondingly. And these are not 3 filters, this is just one filter, which is 3-dimensional, because the input image is also 3-dimensional, RGB. Let us visualize it for better understanding. So this was our 3D image. When we say we are applying one 3 cross 3 convolution filter to it, it means the filter size would be 3 cross 3 cross 3, 3 matrices of size 3 cross 3, one for each channel. So the output will be 3 activation maps, one for each channel, and the final activation map would be the sum of these 3. So one filter will produce one activation map, and if I use 10 filters, then it will produce 10 activation maps. Like in this code, I am using 10 filters in the first convolution layer, and this produces an activation map of 62 by 62 by 10. How? The input image is 64 by 64 by 3. The kernel size, which is also the filter size, is 3 by 3. Now it's a bit implicit since we are not specifying it as 3 by 3 by 3, because it is understood when the image input is RGB, the filter will also become RGB with 3 dimensions. And 3 matrices of size 3 cross 3 will be created. Similarly, if the input is a black and white image, then the filter will also be black and white with 2 dimensions, basically one matrix of size 3 cross 3. Now, how many such filters I am choosing? 10 filters. So 10 filters of size 3 cross 3 cross 3 will be applied to this image of size 64 by 64 by 3. And the activation map produced will be 64 minus 3 plus 1 is equal to 62. 64 minus 3 plus 1 is equal to 62, comma 10, because we have 10 filters. Imagine this as a 10-dimensional image that will be given as an input to the next layer, which is max pooling. Let us understand what max pooling does. So max pooling is the second step in the CNN, and this step further reduces the image size significantly. The input for this step is the output from the previous convolution step. Let's say the final feature map produced after adding the RGB feature maps is this. So this will be an input to the max pooling layer. Here also, we choose a size of the max pooling filter that scans the matrix. And the max pooling operation is to simply take the maximum value within the filter. For example, if we choose a max pool size of 2 by 1, this filter window will move around this matrix in a non-overlapping way by default and take the maximum of these numbers. For example, here the maximum will be 70, then 67, then here it will be 62, and here it will be 66. The size of the output here depends on the input size 4 cross 2 and the filter size 2 cross 1. Just divide the input size with the filter size. 4 by 2 is 2 and 2 by 1 is 2. So 2 by 2. This is because the default stride is equal to the max pooling filter size. What is a stride? It is the number of values you shift on the x-axis and the y-axis while moving the filter window. Like in this case, you shift the filter window by 2 values for the rows and 1 value for the columns. If you change the stride to 1 by 1, like we had specified for our convolution layer, then this window will move in an overlapping way and result into an output of 3 by 2. So you can generalize the output shape of max pooling layer with the formula output shape is equal to floor of input shape minus max pooling shape divided by the strides plus 1, assuming the padding is equal to 0, which is default. So if the input size was 4 by 2 and the max pooling filter size was 2 by 1 and the strides were 2 by 1 as well, then the output will be floor of 4 minus 2 divided by 2 plus 1, comma floor of 2 minus 1 divided by 1 plus 1. That equates to 2 by 2. Similarly, if the input size was 4 by 2 and the max pooling filter size was 2 by 1 and the strides were 1 by 1, then the output will be floor of 4 minus 2 by 1 plus 1, comma floor of 2 minus 1 by 1 plus 1. That equates to 3 by 2. Let us examine this formula for max pooling in the code as well. Here, we don't specify the strides, so by default it is equal to the pool size. Using these numbers, let's calculate the max pooling output. Input for the max pooling is the output from the previous convolution layer, which is 10 matrices of 62 by 62. Pooling size is 2 by 2 and the strides are also 2 by 2 by default. So the formula says floor of input size minus max pool size divided by strides plus 1, which is 31. Same for the second dimension. So 10 matrices of 31 by 31. Now if I change the strides to 1 by 1, then this output changes to 61. Hence 10 matrices of 61 by 61. Let us go further with this output and understand what happens in the third step, which is the flattening step. This is a very simple step. Just take the numbers from the output of max pooling and arrange them in a one-dimensional vector, basically a single row of numbers. And now your image is ready to be fed to a classification neural network. If you see the code implementation, the flattening step does not take any hyperparameters. It is just rearranging the previous layer output and feeding it to the next layer, which is a fully connected dense layer for ANN. Also, you would have noticed that you can have multiple layers of convolution and max pooling to improve accuracy. However, you can have only one layer of flattening because this makes the data as a single vector and ready to be consumed by the neural network. So to summarize, the convolution step applies one or more filters to every part of the image by performing a dot product with the filter numbers to the image numbers, effectively reducing each window to a single number. The output is a convoled image, also known as the feature map or activation map. The feature maps of RGB channels are summed up to create a final feature map. After this, the max pooling step applies a filter that selects the maximum value under that window and significantly reduces the image. The last step, flattening, takes the output of the max pooling layer and arranges them as a single vector. Now this image vector is given as an input to the classification ANN. So if you see the big picture again, every image has a vector representation that is used as an input, and we know the label for each image, which is the output. Using this data, we train the classification ANN model. Now let's take an end-to-end code walkthrough. I have also provided the notebook in the description. If you follow these steps, then you will be able to generate any kind of image recognition model. So a quick overview of what we are going to cover. First, we will understand the libraries that are required for this case study. Then we will look at how do we read the data, how do we organize the training images and the testing images. Then we'll understand how do we create the CNN model, what are these different layers and what are these different hyperparameters. And then we will train the CNN model on the given data. And once we achieve the accuracy that we desire, we will check the model, we will test the model on an unseen face image, whether it is able to successfully predict that face or not. All right, let's get started. So this is the overall architecture we just discussed. The Python version that I'm using in this case study is 3.10.9. We are printing it using the sys library. Sys.version can reveal what is the Python version that you are using right now in your notebooks. Most of the code should be fine for the later versions, but if you're facing any difficulties, then make sure that you revert to 3.10.9 for a smoother execution. We are installing TensorFlow and Keras. These two libraries are required for you to execute the code that is present in this notebook. And these two libraries are essential for all sorts of deep learning code that you wanted to execute in Python. So Keras is a wrapper library that is written on top of TensorFlow. It uses TensorFlow for all the backend calculations, and Keras makes it so easy for us to implement the neural network code that you can literally define the different layers that we read about and then visualize it in a better way. So make sure that you run these commands, the pip install commands, and the libraries should be installed. It is telling me the requirement is already satisfied because I have already installed these, but for you, it will download the packages and install the packages. It may take 1 or 2 minutes depending upon your system's configuration. So make sure that you finish that. Now in this section, I am reading the data, I'm reading the images data, and I'm organizing it. So if you look at the training and testing folders, what you'll find is there are 16 folders and each folder belongs to a person and different kind of images for that person are present inside the folder. Now, I may not have a huge amount of training data for want of the number of images. So I can take only a sample set of pictures for everybody. I cannot take huge amount of pictures, let's say. So in this snippet, we are using image data generator that solves this issue of only a few images being available for a particular class or for a particular person. So over here, let's say there are 20 images. So by using just 20 images, I can generate many more images by applying certain transformations to it. So I've given the link, you can read more about it. But what the image data generator function does for us is it applies certain transformations like the shearing, the zooming of the images, and the horizontal flipping of the images. So consider this image, let's say. So right now, this is the complete face. Let's say while doing the prediction in a real life scenario, the image doesn't come perfectly like this. The image came to you in this fashion, let's say. So it is only a certain portion of the person's face, like the eyes and the nose. So obviously, if you have not showcased these kind of inputs to the model, it will fail. So what this zoom range will do is it will zoom the image a little bit and generate a new training image for the model by using the original image. Similarly, it can shear the image, like tilting the image by 10% or 20%. So it can rotate the image a little bit. So I have the information of the real life scenario when the image is not coming straight, it is coming in a tilted way or flipped way. Similarly, the horizontal flip, it can also flip the image by 180 degrees. So these are different kind of transformations that can be applied, and more number of images can be generated using the existing set of images. So it solves an important problem of low amount of good quality data. It can generate a lot of different images based on only sample images given. And what is this rescale? So rescale is essentially a way to speed up our learning. The image data, the backend data of every image will be pixel values, and it will vary between 0 to 255. So what this rescale will do is it will normalize it. It will convert 0 to 255 range to 0 to 1. So when you have small numbers, it's faster to train the neural network rather than having these big numbers. So it rescales them. So it allows us to train the model fast. So first I'm generating an object. I'm instantiating an object called train data generator or training data generator. I am providing a path. This path is nothing but the final training images. So there are two folders. If you have downloaded the face images from the notebook link that I have provided, you might have seen that there are two folders, final training images and final testing images. So I'm choosing the final training images folder and providing this path. What I intend to do is I want to read all of these images present in the final training images folder into Python. So I'll have to provide the training images path. Similarly, I'm defining validation data generator. So while we train the model, we also want to see whether my model is able to successfully learn or not. So during the training, what we'll do is we will pass on the validation data along with the training data, and we'll make sure that we record the accuracy, how much the model is able to correctly predict from the validation set. Now, for this case study, I have used the validation dataset and the training dataset as same because image data generator allows me to kind of do transformations and generate more images. So only the training path is okay. In an ideal world scenario, you should use different set of images for training and different set of images for validation. So this part is defining how we should generate the training images, and this part defines how we should generate the validation images. Now notice that we are not supplying any sort of shear range, zoom range, or horizontal flip in the validation data range. So we are doing all sorts of transformations on the training data set so that we can train the model on all scenarios, all difficult scenarios. And then while doing the validation, we provide the images without any transformations to just see whether the model is able to successfully predict or not. If we do the transformations in the validation as well, then we might not be able to really judge whether the model is successfully learning the images or not, because we are making it difficult for the model to predict here. So that's why we don't do any transformations in the validation data generator. Now, this portion is just the defining of the object. I'm defining a training data generator object and a validation data generator object. Then to generate the actual data, the training set and the validation set images, I am using the flow from directory command from the train data gen object. And what it says is, give me the training path from where I should read the data and what is my target size. So all of these images, if you just check any one of them, if you inspect, these are like 355 cross 355 in dimensions, okay, roughly. So this data can also be very taxing in terms of compute. And what we can effectively do is we can resize that 300 pixels or 355 pixels to 64 by 64 pixels. That will significantly reduce the amount of computing power required. Since our laptops are, not huge servers, so that's why we can use this configuration to reduce the incoming image to 64 by 64 pixels. So the target size is provided. You can keep it more, you can keep it like 120 or 200 depending upon your system's configuration. If you have good computing power, you can keep it. And the more training size you use, the better the model will learn, because you'll have more data to learn about those images. So I'm using 64 and it still works fine. Now batch size is 32. So how do we read the images? There are multiple images. In fact, there are 244 images. So in a batch of 32, we should read the images. And the class mode is categorical. So each face, each person will receive one class associated with it. Like for example, face 1 here became 0 class. Phase 10 became 1 class, so on and so forth. So the class mode to read the data is categorical. Same thing for the validation set. We need to make sure that the validation set has the same type of target size as compared to the training set. If you change these numbers, then the model will suffer and will not be able to generate correct predictions. Then over here, after reading this, we are printing the class indexes. So if I run this, I'm able to read 244 images belonging to 16 classes. There are 16 folders, 16 people, so there are 16 classes, and overall 244 images. So every face, as I mentioned, has got a label associated with it, a class associated with it. It's a dictionary which is in the format of face belongs to this class. And for our predictions to happen, we need this the other way around, like 0 class belongs to phase 1 or 1 class belongs to phase 10. So this is the key and this is the value. We would want to flip it. So in the next section, this is what I'm trying to do here. First, we take the train classes using training set dot class indexes. So this train classes object is nothing but a dictionary that stores this information. Okay. Then I am creating an empty dictionary result map, and using a for loop, what I'm doing is I'm simply flipping this. So I'm doing a zipped iteration. Two variables define face value and face name. And what I'm doing is I'm just iterating train classes dot values. So what will be the train classes dot values? So 0, 1, 2, 3, 4, these will be the values. And train classes dot keys. These are the keys, phase 1, phase 10, phase 11, so on and so forth. So I'm just saying, first take the phase value, which is 0, 1, 2, 3, 4, and then provide it against the phase name. So I'm just reversing this information. And in the result map, what I will have is a mapping that says, okay, 0 class means phase 1. 1 class means phase 10. So this will be helpful when I'll do the predictions later on. So this result map can be stored as a pickle file. So you might know that pickle is one of the formats that allows us to compress our models and any object in Python into a compressed file that can be read very fast. Okay, that can be stored for your deployment. So what we are doing is we are using the pickle module and we are opening a connection to our OS, and we are creating this results map.pickle in the current folder, in the current working folder. You can provide a path here if you want a specific path for this to be saved at. Then write in binary mode, and in this file stream, with this stream open, we are dumping the result map. So result map is a dictionary that we are dumping in this result map.pickle, and we are using the highest protocol. That means the highest compression. And here we are printing that what are the different classes and what is the face belonging to that class. Now notice that I have created a variable called output neurons that I'm going to use later on. In a classification neural network, the output layer or the number of neurons in the output layer is defined by the number of classes. Since we have 16 different classes here, since we have 16 different people, 16 faces, that's why the output neurons must be 16 as well. So when you see we are defining here, then the output layer will contain output number of neurons. So this dense layer. Okay, so this will be 16. So in the next section, we are defining the CNN model. Now a lot of it we have briefly seen while I was describing the concept of CNN to you. First, we are importing all the necessary layers from Keras. Sequential is required to define the overall model. Then the convolution layer, max pooling layer, then the flattening layer, and the dense layer, which is used for artificial neural network classification, okay, as well as regression. So first we are initializing the convolutional neural network model using the sequential function. Then we are adding a convolution layer. We can add multiple layers of convolution. Here I have added 2 layers. This is the first layer, and then the max pooling, and then the second layer, and then the max pooling. Can I add one more? Yes, you can just simply take this, you can paste it here, and there will be a third layer. So you can add as many layers of convolution and max pooling as you want, but keep in mind, the more layers you add, the more computation is required to train the model. Okay, so deleting that. So let's observe what we are doing here first. So convolution 2D is the function, and I'm adding this layer into the sequential empty object, basically the convolution neural network I'm started. I'm using 10 filters. So we discussed that you can define any number of filters here. So we should start with a lower number. You can ideally start with 5 filters or 10 filters, and then keep increasing this filter parameter till you achieve the highest accuracy that you're tracking over here. Then we define the kernel size or the filter size. So 3 cross 3 is the filter size. Now, we also discussed that if my input image is 64 by 64 by 3, then by default the kernel size that gets initiated is 3 cross 3 cross 3. So it is not explicitly mentioned here, but it is understood that if your input image is of 3 dimension, then your kernel size will also become 3 dimensions. So your kernel size really over here will be 3 cross 3 cross 3, 3 comma 3 comma 3. Okay, so I am using 10 filters of 3 cross 3 cross 3, and the strides, the way it moves horizontally and vertically, is 1 cross 1, so 1 pixel at a time. Then I am also providing the activation function for this layer. It is relu. It is recommended to use relu during the training phases, and then later on we use softmax because we have to predict the probability. The second layer is the max pooling layer. Here I am specifying the pool size of 2 cross 2, and by default the strides will also be 2 cross 2. If you look at it over here, the strides are given none. If you see the definition, by default it takes 2 by 2. This will significantly reduce my image. It will process it as we discussed. Then I'm adding another layer. So you start with a large amount of filter, and then you can keep decreasing it. So that makes kind of a cone shaped neural network. In the subsequent layers, typically you use less amount of filters as compared to the previous layers. So you keep focusing more and more and keep compressing the image more and more. So I've added the additional layer, the second layer. Now notice that I don't have to provide any size information over here. In the max pool as well, I don't have to provide the input shape. Why? Because it is understood that what kind of image will be given as an input. So if you notice, the input to convolution layer, the first convolution layer is 64 by 64 by 3, and then the output of that layer became 62 by 62 by 10. Why 10? Because I'm using 10 filters. So the image that came in as an input was 64 by 64 by 3, and then it became a convolved image of 62 by 62 by 10. All right, that is the input that is given to the max pooling layer. So max pooling takes that input, this input, and then max pooling further compresses the image, and the image becomes 31 by 31 cross 10. So 10 matrices of 31 by 31. Similarly, this is the input for the next layer. So this convolution layer, I don't have to specify what is the input layer, or even in the max pooling step, I don't have to specify what is the input layer because the network definition takes care of it. Okay, so this convolution layer takes the input 31 by 31 by 10, and then it reduces it further to 14 by 14 by 4 based on the formula that I discussed previously in the video. Okay. Then once again the max pooling further reduces it. It takes the 14 by 14 by 4. Now why 4? Because we are using 4 filters here. That's why the image was reduced to 4 matrices of 14 by 14. So max pooling further reduces it and it became 7 by 7 by 4. Now flattening step essentially takes all the numbers present in these matrices like 7 by 7 by 4 and it flattens it. So 196, 7 into 7 into 4, 196 numbers are created as a single vector like we saw previously in the video. And this is the input that is given to the classification model. So how many neurons I'm defining here in my first hidden layer? So I'm using the dense function and I'm using 64 neurons in my first hidden layer, and I'm using just one hidden layer over here. You can keep more hidden layers as well if you want to. You can add one more, two more, and you can decrease this value to let's say 32 or maybe 16. Once again, the cone shaped neural network, you can create this. But I guess I'm getting the accuracy just by adding one layer, one hidden layer, so I'm not bothering to add more layers. Once again, using the same rule, you need to find the accuracy using the least amount of neurons, least amount of layers as possible, because the more neurons you keep, the more layers you keep, the more computation is required. Then the output layer has to be defined, and as I mentioned, the number of neurons in the output layer will be equal to the number of classes. So here my classes are 16. There are 16 different people, so 16 neurons, or I can write 16 over here, or I can define that variable output neurons. So I'm using the variable output neurons. Here I'm using the activation function as softmax because I need the probabilities as the output for every prediction for every class. And from that, I will choose which class has the highest probability as my answer. Now compiling this CNN, so I've given two options here. This is commented because binary cross entropy is the loss function we use when we have a binary classification scenario. Like if there were two people, then we would have used binary cross entropy. But there are 16 people, so there are multi-class classification happening. So we are using categorical cross entropy. Optimizer is Adam. You can use RMS prop as well. And the metrics that we are specifying over here is the accuracy metric that we want to track. All right, so let's define this. So classified or summary tells you what are the different output shapes and parameters that are used in the neural network that you have defined. Here, the CNN network that we have defined, it consists of these different kind of parameters. So the final output layer will produce 16 numbers, 16 probabilities for me, 16 outputs. So now it's time to train the model. I'm using a time module here to record how much time it is taking for me to fit the model. I'm taking a timestamp here, the start time and the end time using the time method. And then I'm simply subtracting the end time minus the with the start time and dividing it by 60 because the end time and the start time will be in seconds. The difference will be in seconds and it will give me how many minutes it took to train this model. Now, depending upon your system's configuration, it might take less amount of time or more amount of time to train the same model. So how are we exactly training the model? So classifier is the object that we just compiled above, and we are using the fit method associated with it to train it. Now what we provide the training set, the image generator that we have created above, and we provide the hyperparameters along with it. So let's understand what are these hyperparameters. Each one of them has a specific function. So first of all, steps per epoch. So steps per epoch is 8. Why is it 8? So by default, the batch size is 32. So if you see here, the batch size is specified as none. And over here, if you see, if unspecified, batch size will be defaulting to 32. And we should not specify the batch size if we are providing image data generators. So the batch size is 32 and the total number of images that we have is 244. So 244 by 32 is 7.6. So at max, the steps per epoch can be 8. But what does it really mean? So if you run this, you'll see that 8 images are being passed here. See, after every 8 image, it goes to the next epoch. So we have 60 epochs present here. That means we are changing the weights of the network that we have 60 times after one epoch is finished. So when you have passed on 8 images to the network, then it calculates the error again, and then based on that back propagates and changes the weight. So this process is repeated 60 times. That's what we say, 60 epochs. So this number cannot be more than 8. If you provide more than 8, for example, let's say 10, then it will exhaust the amount of data that is present in your training samples. So it'll go and it'll say, okay, we are running out of the data because you provided a batch size which is greater. So batch size into your steps per epoch, it is exceeding the training samples. So that is why we should provide it less than 8 that we just calculated, like 244 divided by 32 is like 7.6. So at max we can provide 8. So when we are running this, what's happening is every epoch is taking the validation data as well and 4 images from the validation set. So we created 2 sets of image data generator, like training set and validation set, right? So to evaluate how the model has learned the training data, we use the validation set and calculate the accuracy. The metric that we have specified here is accuracy. So we calculate this accuracy and check what is the validation accuracy and what is the training accuracy. Now it's showing 1 because I ran it multiple times. Let me restart it over here. Yeah. So you see it starts with an accuracy, let's say 7%, and then it improves to 11%, then it improves to slightly more, and then it keeps going on and on and on till the accuracy will reach 1 or till your epochs are finished. Okay, if you have specified a threshold, then it'll stop there. Otherwise, it'll just complete the 60 epochs and whatever accuracy you have achieved till 60 epochs. So how did I arrive at 60 epochs? So I did a little bit of parameter tuning. I tried different sort of epochs. Like I tried 10, 20, 30, 40, 50, 60, 70, 80, different type of epochs. And then finally, I saw that while I do 60 epochs, I'm almost nearing to 100% accuracy. So that is something which I have chosen. So validation accuracy is also 100% and training accuracy is like 100% and 99%, which is good, which is very good in fact, because now I'll be confident in recognizing all those 16 peoples if I give a random new image of the same people. So this is how we train the model, and all of these are hyperparameters that we must tune, like the number of epochs, the validation steps per epoch. Like it could be lesser as well. You can have 5, you can have 6, 7, 8, less than 8 because of this output. And similarly over here, all of these are hyperparameters, like what number of filters you are applying, what should be the kernel size, what should be the strides and the activation functions and different layers. All of these numbers are your hyperparameters, like over here the dense layer as well, except this, because this is defined by the number of people that are present in your classification case study. So 16 faces, so this will be 16, but rest of it is like you need to try out different values, and then that is what is called is tuning the network according to your data. So if let's say you are applying this template on some data sets that you want to classify, let's say you are doing rock paper scissors or any other case study that you have for your project, then you will have to tune these parameters to get the highest possible accuracy over here. I mean, the ideal goal is to get 100% accuracy, but in majority of the practical data sets, you are not going to get 100% accuracy. If you are getting 80 to 90% accuracy, then you are lucky and that model is a very good model. Then once we have trained the model, then this classifier can be saved for future references. Like over here, I can save this model using the save method, and it has an inbuilt way to save the pickle file. So the save method allows me to save a model, the classifier model, using a pickle format. So yeah, this is saved in my current working directory as classifier.pickle, which I can load later on. What is the usage of this saving? So when you deploy your predictive models, you cannot retrain them every time. So what you need is a trained model and just do predictions on top of it. So this pickling or saving the model actually allows you to just load the model and do the prediction. It improves the prediction times because this pickle file also loads very fast. Now, over here, we are testing whether the model is able to predict the images correctly or not. So remember, we had two types of folders: training images and testing images. So training images that we have used so far contained various samples of the person's face. And over here, the testing images also contains the samples, but less number of samples. Let's say over here, four images of every person, and these images are not seen by the model. I mean, similar faces are seen, the other pictures of the same person are seen, but these exact pictures are not seen. So these are fresh images, these are new images that the model has not seen, and that is the real test, whether the model is able to predict on a totally unseen image or not. So we're going to use one example here. Let's say phase 4. So this is like phase 4 and I'm loading one of the phases. So I'm providing the final testing images path and phase 4 and to phase 4. So if you see, so this is the image I'm loading here, right? So how do we load? We provide the test image path where the image is present along with the exact image name, and we are using the image module from Keras pre-processing. It will help us to load the image. So the test image that I'm loading here is image.loadImage test image path. This is the path, and the target size is 64 by 64. Why the target size is 64 by 64? So the model that we have trained is based on certain images, right? And these images were 64 by 64 size. If you don't load the same size of image while doing the predictions, the model will get confused that what are these different kind of numbers I'm getting, and it will throw an error. So you need to make sure that your target size is exactly same as your training data set, all right, while doing the predictions. So even though my original images will be higher, let's say here, just like we did in training data, the original image over here is 316 by 316 pixels. While I load this, I make it 64 by 64. So see, it becomes so tiny here. Test image is this tiny image, like 64 pixels by 64 pixels. Now I'm going to pass this to the classifier model we just trained and see whether the classifier model tells me this is phase 4 or not. Okay. And since we have almost 100% accuracy, so I'm pretty sure that it will predict correctly. So how do we do the single prediction? So this test image cannot be directly passed on to the classifier. What you need to do is to convert this into the same format in which the data generator has given the data to the model while training. So there are a couple of steps we need to take. First, we are converting the image into a numeric array, the 0 to 255 representation. So every pixel value present in this image will be represented with an array of numbers, like 3 numbers, red, green, and blue. So we convert this using image to array function from the image module. So I'm passing the test image and converting it into a numeric array. And if you can see here, I'm printing the shape after conversion. The shape is 64 by 64 by 3. So 3 arrays of 64 by 64, the red, green, and blue channel. Then since we are just doing one prediction right now, so we need to reshape this for one single prediction as one single sample. So I'm reshaping it as 1 comma 64 by 64 by 3. So one sample of 64 by 64 by 3 by using numpy.expand dimension function. Okay, we give this and we say that the axis is equal to 0. That means one sample of 64 by 64 by 3 has to be created. So test image array expanded dimension. And then now this particular image will be ready for prediction. So this array is what we provide to the model. So test image array expanded dimension, verbose means do not, verbose equal to 0 means do not print the log. So this prediction will produce a result, and this result is nothing but the probabilities. Remember, when we were defining the model, we said that the output has to be with 16 neurons, right? So it will produce an output that has 16 probabilities, the probability for each person. So here it is predicting the probability over here. So you can see, literally you can count, like, since this is a small data set, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10th index. And over here you can see where is the 10th index. So 10th index belongs to phase 4. In this dictionary that we saved previously, the result map, 10 belongs to phase 4. So that is what the model is answering, that this is phase 4. So it is doing the correct prediction. Okay, so how exactly we are doing this? So we are taking the result and we are saying which particular position has the highest probability. So numpy dot argmax will give you which particular position has the highest number associated with it in the result. And then we take that number, let's say this output is 10. We are passing 10 to the result map. So if you pass the key 10 to the result map dictionary, it will return you the value of it. And the value at 10 is phase 4. So this is how we can get phase 4 over here. All right. And you can change it. You can change, let's say, let's try another one. Let's say one phase 4. So one phase 4 will be this image, whether it is able to successfully predict this image or not. Let's see. So yeah, we loaded the another image and yeah, it is still able to predict. It is phase 4. All right. So, I mean, this is the overall structure with which you can generate any kind of face recognition model. You have to just make sure that you organize your data properly into training and testing folders. Okay. And then use the training folder images to train the model and testing folder images to just check whether it is able to successfully predict or not. So now let us take a look at the additional code snippets that I used previously in the video to explain the concepts, like how do we look at the backend numbers for an image. Here we are loading the phase 5 and using the image module from Keras preprocessing, providing the image path, and then using the load image function again. Okay, here we are providing the target size of 500 by 500 just to see like how many numbers are required to store such kind of an image. So 500 pixels horizontally, 500 pixels vertically. This is the image, and we can print the backend array of numbers using the image to array function from the image module. So we are passing the test image here that we have just loaded, and it produces the array. And we can look at the shape of this array by using the shape attribute. So 500 by 500 by 3. So 3 matrices of 500 by 500 pixels, essentially containing the RGB information. Every pixel has red, green, and blue information. All right. So how many such numbers are total numbers are needed to store this image? So we saw previously that it needed 750,000 numbers to store just one image. And then we calculated a bunch of other statistic, like how many values are needed to store 1 megapixel and 50 megapixel image. And if you had 5,000 such images, then you are basically dealing with 786 billion values just to process it, and it's huge and it requires a lot of computational efforts. So what we are doing in this section is we are creating a CNN model that is only working till the flattening step. In the previous section, we created a model till compiling it and training it with a classification neural network. But I'm stopping only till flattening because my interest here was to see what is the representation given by CNN model. Like over here, so there are total 4096 pixels over here, and it needs 12,288 numbers to store this image. So can CNN reduce this? Yes. So we saw that CNN can store this particular image using 128 numbers only, or if I change the hyperparameters, it can store even with less amount of values. Let's say Over here it is using 4 by 4 max pooling. If I say 6 by 6, then the output over here of the flattening step is 64. That means I'm able to represent these 12,288 numbers only by 64 numbers. So this is the kind of reduction it can bring. Okay, and how we are doing that? Once again, we are first loading the image using 64 by 64 target size and load image function from the image module. Okay, and then we calculate total number of pixels are 64 horizontal, 64 vertical pixels, so 4096, and each pixel has 3 values associated with it. So 64 by 64 by 3, 12,288. And then we are just printing it here, the backend array that is stored there. So image to array function is utilized to generate the backend array of any image that you have loaded. Okay, and that we are printing it over here and printing the shape of it. And then we essentially pass this image to the classifier that we just defined above, and it will essentially predict. And what it will predict, it will not predict the probabilities of 16 faces, because that is not what we are doing here. We are compiling it only till the flattening step. So it will just flatten the image and give you the output. So this is what exactly is happening. It flattens it and produces the image vector. Just for you to understand what are the different type of values that gets produced for this image when we pass it to CNN. And this is the image vector that is given to the classifier ANN that we created above to train against the label Y. All right. And we also compared it with the output of other person's face, like over here, these 64 numbers, and then compared with another person's totally different person's face. So how these 64 numbers are faring against the other person's 64 numbers or 128 numbers, depending upon the network size. So we compared these numbers with different persons. So I have provided this notebook in the description of the video. Please make sure that you download and practice it. The more number of times you apply this template to different scenarios, the more you will learn about CNN. So all the best for that. And if you have liked this video, then please share it with your friends and spread the knowledge, and consider subscribing to the channel for more such videos in future. This is Farooq Hashmi from thinkingneuron.com. Thank you so much for your time.